to write the equation of a plane in space, and this one's actually going to be one equation that has the x, the y, the z in it. This is the most basic equation that has the x, y, z all together. So in the plane, the most basic equation that has the x and the y together is the equation for a line. The most basic equation in space that has x, y, z together is the plane. In order to write the equation for a plane in space, we need a point in the plane, which we're calling P, which has coordinates x sub 1, y sub 1, z sub 1, and we need a vector that is normal to the plane. We can't just have a vector that is in the plane because that only represents one direction. And technically, a plane has two directions. If you think of the xy plane, the x, what's the word I'm thinking? The x-axis is one of the directions and the y-axis is one of the directions. So a plane always actually has two directions in it. So we can't just have a vector in the plane, we need a vector normal to the plane. So a vector that is normal to the plane could technically come about from a cross product between two vectors in the plane. So two vectors in the plane, if we crossed them, would give us a vector normal to the plane. And we can use that one vector that's normal to the plane to represent the plane. The point in the plane and the vector normal to the plane. So the technical definition for the equation of the plane is the dot product between the normal vector and the vector PQ, wherever that is equal to 0. When is a dot product equal to 0? When it's 90 degrees, right? So I want this dot product to equal 0. So I know that my normal vector should always be normal to the plane, which means this PQ vector should always be in the plane if it's going to be normal. I know P is in the plane, which means this vector Q should always be in the plane. And we're going to let Q be arbitrary. Q is just our arbitrary XYZ. So the plane is represented by the dot product between the normal plane and the vector PQ, where Q is an arbitrary XYZ and P is a point in the plane. Every time that dot product comes out to be 0, we have the equation for our plane. So what this looks like, and you don't have to work this out every time, this is going to lead to an easier formula that we can actually do. Vector PQ, we're going to do the Q's minus the P's. So this is going to be X minus X1. Y minus Y1. Z minus Z1. And then when we dot that with n, remember we multiply corresponding components. And n is our direction numbers that are normal to the vector, a, b, and c. So this is going to be a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. This is called standard form for the vector, or for the plane. This is standard form for the equation of the plane. So we see those direction numbers, a, b, and c, from the normal vector, and we see the coordinates x1, y1, z1 from the point. But if we want to, there's a little bit of algebra we can do. We can distribute the A, the B, the C, and that will give us some like terms to combine. So really, if we want to clean this up a little bit, we could write this as AX plus BY plus CZ equals D. Because A times X sub 1 is going to be a constant, B times Y sub 1 is going to be a constant, C times Z sub 1 is going to be a constant, and we could combine them all together and move them to the other side. That is called the general form for the equation of a plane. And don't think of it as two different formats that you have to remember. The way that we get the second one is just by continuing to simplify the first one. So we're going to find the general form for the equation of the plane containing the point 0, 5, negative 2 that is normal to the vector 1, 1, 3. So there's not much work to do on this one. This is just to get us familiar with the format and what to do with our different numbers, where each of them goes, what the setup is, and then we'll work our way up to some more difficult problems. So 0, 5, negative 2 is in the plane. And if you want to think of it this way, any other random point Q that's also in the plane, we can create a vector between P and Q, and that vector will always be in the plane. So if we do a dot product between this vector that's in the plane and the normal vector, they will always be 90 degrees apart. So that dot product will always be 0. So 1 times x plus 1 times y minus 5 plus 3 times z plus 2 will always equal 0. This is the standard form. You don't have to set it up like the dot product. You can just remember the standard form we have up here, where you do A times x minus your x coordinate, B times y minus your y coordinate, C times z minus your z coordinate. But that's where it comes from. If you take your point and then just any other random point, which we represent as x, y, z, and we create a vector out of them, and we say that is any vector in the plane, and we dot it with the normal vector, it's always going to have a dot product of 0. Because they'll always be 90 degrees apart. That is standard form. Just leave it like that is standard form. We want general form, which means we want to do some simplification on that. So 1 times x is just x. 1 times y minus 5 is just y minus 5. And then we can distribute the 3 and the z plus 2. So we get plus 3z plus 6. And we've got some constants we can put together. We've got a minus 5 and a plus 6. And then we also want to move it to the other side of the equation. It's going to move to the other side as a negative 1. So on the left, it's a positive 1. It's going to move to the other side as a negative 1. So it's x plus y plus 3z equals negative 1. What were the components for the normal vector? 1, 1, 3. What are the coefficients on x, y, z? So even after we do the algebra to get it into general form, you can still see those components. The 1, 1, 3, we still see them here. So you can still look at the equation for a plane and look at the coefficients and figure out what the normal vector is. What we can't see is what point got used. Because we distributed and combined, we can't see the point anymore. But we can still see the normal vector because it's the coefficients. Okay, so that's the equation for our plane. X plus y plus 3z equals negative 1. We're going to find the general form of the equation of the plane that contains the point negative 2, 1, 7, and the vectors r equals 102 and s equals negative 2, 1, 3. We want the plane that contains all that stuff, that point and those two vectors. What sort of information do we need to start writing the equation for a plane? There's two things that we need, a point and what kind of vector? We need a point and a normal vector. What does normal mean? There's two other synonyms for normal that we keep using? Orthogonal, and what's the old-fashioned word that we learned in perpendicular? So we need a point and we need a normal vector. They gave us a point, they did not give us a normal vector. They gave us two vectors that are in the plane. How can we find a normal vector? We're not going to do standard position. We would need 2 points to do standard position. Cross product will give us a normal vector. The cross product of two vectors gives a normal vector. Cross product of two vectors is a normal vector. And if those two vectors are in the plane, the cross product will be normal to the plane. So we want to do R cross S or S cross R. Either one, doesn't matter. So R is 1, 0, 2. S is negative 2, 1, 3. So for the I's, I'm going to do 0 minus 2. So I've got negative 2I. For my J's, 3 minus negative 4, which is 3 plus 4, which is 7. And the J's change sign, so this is minus 7J. And then for the K, I've got 1 minus 0, so plus K. The equation for a plane is unique. So if you did S cross R, cross product is not commutative. If you did S cross R, you would get a different vector. You would get positive 2I plus 7J minus K. But your equation, your final equation for your plane would be equivalent. If you use a different point, if you had multiple points to choose from when you set up your plane, your final answer would still come out the same when you set up the equation for your plane. So you won't get multiple answers that are all correct when you set up the equation for a plane. There's only one answer. So I'm not going to set up all that dot product stuff. I'm going to go straight to the format. So those direction numbers give me my coefficients, and inside the parentheses, I'm going to do the variable minus the point. So the direction number for x is negative 2, and then x minus our x coordinate, which is negative 2, so x minus a negative 2. The direction number for y is a negative 1, and then y minus your y coordinate, which was 1, and then the direction number for z is 1, times z minus your z coordinate, which is 7. So the numbers in front are the components from the vector. The numbers inside, we're subtracting the coordinates from the point. So the components from the vector were negative 2, negative 1, 1. Negative 2, oh, whoops, that's negative 7, sorry. Negative 7, 1. Negative 2, negative 7, 1. Negative 2, negative 7, 1. Sorry about that. And then the coordinates from the point were negative 2, 1, 7. Negative 2, 1, 7. And we need to simplify this because we want the general form. So that's really x plus 2. And if we distribute, we get negative 2x minus 4 minus 7y plus 7 plus z minus 7 equals 0. How would you find the equation of a plane if I gave you 3 points? So think about what you need and how we can get there. We're going to have to do a cross product. We can't plug points into a cross product. Vectors go into a cross product. We're going to make 2 vectors, and then we're going to find their cross product. That's going to give us a normal vector. So if you're given 3 points, you're going to use those 3 points to make 2 different vectors. And then you're going to do the cross product of those 2 vectors. That will give you a normal vector. At that point, you'll have a normal vector, and then you'll have 3 different points to choose from. And what do we need to set up the equation for the plane? A normal vector and a point. So we're ready to go. Yep, so all you have to do is use those 3 points to set up 2 vectors, and then do the cross product of those 2 vectors, and you've got your normal vector.